it's time to generalize. So let's say that the functional will be generalized to surfaces through which an infinite set of electron rays pass through perpendicularly. So let's generalize that functional to a function such that the different constant of that function will define wavefronts of electrons for fixed time. So let's take an initial surface and fix the energy of the electron, which is equal to kinetic plus potential. We take each point on the surface and we find its normal. So the normals are at 90 degrees from the surface. So they are all at 90 degrees. And then we extend that surface to subsequent surfaces by choosing electron paths with fixed energy to pass through parallelly to those normals. So they have to pass through each point of the surface. These are all valid electron paths that have fixed energy and pass through the surface perpendicularly. Now, if you extend those paths, and then you construct further surfaces that are perpendicular to those paths, you will find that those wavefronts have to be defined by a constants of the generalized action function for fixed time. S is not a time. It's a value of action. This was for light rays. The phi was defined as something that was equal to 2 pi f delta t. So we were concerned with time as defining the phi that determined the wavefronts. But now we want the wavefronts to be determined by an analog to time for light rays, which is the action, which is so we want now that the wavefronts have to be defined by surfaces of constant S. In our case, the potential is time independent, which means the potential will be equal regardless, it will be equal at the position regardless of the time. So we do not need to consider the time. So we want S to be something that gives the value of an action. We want S to be defined such that, suppose you took a point here, call that XF, YF, ZF, and suppose you traced it back to that point, and we call that point XI, YI, ZI. I'm just gonna make it more clear to you guys. And suppose, let's change color. Suppose that this is given by, that surface is given by that, and that surface is given by so we want to define the action such that if you took one of the paths at the final time and you subtracted the value of that function by an initial point, so we define XF, YF, ZF, and XI, YI, ZI as we did here. So XF, YF, and ZF is a point on a further wavefront such that the paths that goes through that wavefront, if we backtrack that path until we reach a wavefront where the time is exactly the time it took for the electron to reach the final point, then you will find that this is equal to which was actually the functional of the path. But the path has to go through these 2 points. We want also that function to satisfy an invariance if we shift the time by something. We still want it to give the same value. We still want that to be equal, even though we shifted the initial time and the final time by the same value. XF, YF, and ZF is a point on a certain wavefront, and this point is part of a path of electron that went through a series of surfaces perpendicularly until it hit an initial point, TF seconds in the past, where TF is the time it took for the electron to go from xi, yi, and zi. So Tf is the time it took for the electron to go perpendicularly from the initial wavefront from the point xi, yi, zi is the time it took to reach finally xf, yf, zf in the subsequent wavefront and cut that final wavefront also perpendicularly. The only way for that to work is, we have to decompose that function into two parts. This is the only way that this condition is satisfied, which is if we added time to the same amount of time to both functions, you would still, the difference of those two functions will still give you the total, the functional value, the variation of the action. It doesn't matter how much you shift the initial and final time.